Hello and welcome to the Homeland Defense and Security Information Analysis Center webinar covering power beaming and space solar innovation. My name is Steve Redifer, and I'm the director of the HDIAC, and today we have the privilege of hosting Dr. Paul Jaffe. I'm grateful to everyone who's taking time out to join us during these challenging and busy times. I'd also like to thank our sponsor, the Defense Technical Information Center. The DTIC-IAC mission is to collect, synthesize, produce, and disseminate scientific and technical information to the DoD and federal government users, and this webinar is made possible through DTIC sponsorship. A couple of thoughts before we start. Please note that all of your lines have been muted, so if you have any questions during the webinar, we ask that you please submit them using the attendee chat box on the left-hand side of the screen. We'll collect up those questions and we'll work to save the last 10 minutes or so of this presentation to go over those questions and discuss them. If we were to run out of time for questions, we'll make note of all the remaining ones and we'll post responses after the conclusion of the brief. Please also note that this webinar is being recorded, and a link for the recording as well as these slides will be available at our website, www.hdiac.org, for later download. And with that, it is my distinct pleasure to introduce to you today's presenter, Dr. Paul Jaffe. Dr. Jaffe is a researcher and electronics engineer at the Naval Center for Space Technology at the United States Naval Research Lab. In over 25 years at the Naval Research Lab, Paul has led or held major roles on dozens of space missions and breakthrough technology development programs for agencies such as NASA, NOAA, DARPA, as well as the DoD. Paul has also served as a coordinator of the NRL studies of the military applications of space solar, and he was the principal investigator for a groundbreaking 4-year research effort involving the development and testing of modules for conversion of sunlight into microwaves. The modules have a number of potential applications, including satellites for space solar, and are slated to be tested in space via the Department of Defense's Space Test Program. Paul has presented to a range of audiences on science and technology topics and has appeared worldwide in television, radio, print, and online media as a science and technology expert on outlets such as MSNBC, the Science Channel's Through the Wormhole with Morgan Freeman, the EnergyCast podcast, and as a TEDx speaker. His work has been featured by Wired, Der Spiegel, CNN, the Huffington Post, the Drudge Report, Political, and dozens of other outlets. Paul received his Bachelor of Science in Electrical Engineering from the University of Maryland, College Park, and a Master of Science in Electrical Engineering at the Johns Hopkins University, where he graduated with honors. Paul earned his PhD in Electrical Engineering at the University of Maryland, College Park, where he also serves as a lecturer for the Aerospace Engineering Department, teaching a graduate course titled Power Beaming and Space Solar. It is my distinct pleasure to host Dr. Jaffe today. With that, the floor is yours, Paul.
Steve, thank you for the introduction, and thank you also for the opportunity today. It is my pleasure and honor to be able to speak to folks today. This is a topic that, as you mentioned, I have been involved in for quite a few years at this point, over 10 years, and I think that the prospects for it moving forward are tantalizing, and it's important for people to be aware of them and understand the implications. So let's see, I'm looking for the little arrow for me to click. Do I have control of the charts? There we go, okay. Okay, so first thing, I'm gonna be talking about two distinct things today. The first one is power beaming, as evidenced by the picture you should see on the left of your screen. And the second thing is space solar, which is the picture on the right. If you don't really know what either of these are right now, that's fine. That's why we're talking about this today. But there's often conflation of these two things, and I just want to be crystal clear that they are distinct and they have distinct usage contexts and applications. Next chart, please. All right, so let's start with some definitions. Nomenclature is often a point of confusion, and we want to nip that in the bud. So what is power beaming? As I talk about power beaming today, it is going to be defined as the delivering of meaningful amounts of energy without moving or employing mass between the transmitter and receiver. So if we look first at two different places, we often have a hard or expensive place to get energy, pictured on your right. This might be a drone in flight, or it might be a remote research station or forward operating base or combat outpost. And then on the left, we might have a comparatively easier place to get energy, such as the utility grid or a generator or some other source. Oftentimes, these two locations will be separated by some distance that is ill-suited for a physical connection. Enter power beaming as a potential way to connect them. Not necessarily always the top choice, but certainly one that we should be aware of and that I think a lot of people simply aren't at this point. Now, we can break that simple 3-block diagram into this sort of 6 or 7-block diagram, depending on how you count the media between the transmitter and the receiver. And I won't go into great detail of all of the different callouts here of the parameters, but suffice it to say that it is important to have quantitative measures for the performance of the various parts of the system to figure out whether it makes sense for your application. Perhaps the 3 most important things are the power you put into the transmitter, the power you get out of the receiver, and the distance that can exist between them. Generally speaking, power beaming is going to operate in a point-to-point sort of mode where there should be a clear line of sight between the transmitter and the receiver. It's not exactly true, and there are definitely instances where you can go around corners and the like, but in general, the connection between the transmitter and receiver is line of sight. Now, there are a number of different parts of the electromagnetic spectrum that are of interest for power beaming, and they are defined largely by where these waves can travel without being absorbed or dissipated. So the picture I have on the right side of the screen shows atmospheric opacity, how much the atmosphere blocks a wave, an electromagnetic wave's transition. And you'll see there's an upper sort of pink purplish box that highlights the optical region. This is where we might use lasers for power beaming. And then lower down, there's a blue box that highlights the millimeter wave and microwave regions of the spectrum. You likely know that light and radio waves are all different expressions of electromagnetic waves that occur along the spectrum. That includes everything we use from cell phones to X-rays and even getting higher to gamma rays. For power beaming on Earth, in the atmosphere, these are the windows of greatest interest because we don't lose as much energy in the transmission itself. Sometimes there actually might be applications where it would be better to limit the range to avoid interference, but in general, these 3 modalities, laser, millimeter wave, and microwave, are where we look to implement power beaming. Now, this has been done on numerous occasions. I could spend easily many hours chronicling all of the different power beaming demonstrations that have been done over time. Many people often think about Nikola Tesla when they think of power beaming and wireless power. That is a little bit different than what we're talking about here, and I think just for the purposes of this discussion, I'm going to focus on some things that are a bit more recent. I'll first talk about some of the things that have been done on the laser side. So in the upper left of your screen, you should see a green laser beam going from a laser to a small rover. This was done by the Europeans in 2003 to demonstrate power beaming to a craft or rover that you might use in a planetary crater or on a planetary surface. This is something that has enjoyed a real resurgence in interest recently because we're going back to the moon. The moon's nighttime lasts 2 weeks. Its daytime lasts 2 weeks as well. But there are craters that are shadowed such that they never see any light at all, and they get very, very cold. So if you were to just send something battery powered in there and it ran out of battery power, it might never come back because it would just effectively freeze to death. So this use case is enjoying a real renaissance right now. In the upper right, you can see a quadcopter that has what looks like a solar panel, and that's also being illuminated by a laser. And this was a demonstration that was done by the Japanese in 2007, showing that if you had a disaster and you needed to spend a long time searching for victims, and there's a sort of simulated disaster zone below the quadcopter, and actually there's a camera on this quadcopter pointing downward that reveals a victim in need of rescue in this debris. So this is another concept where right now drones are limited in the amount of time that they can fly, and here's a way where we can extend the flying time of a drone effectively forever, until it wears out, really. On the lower left is a picture from a demonstration that was done in 2012 at the University of Maryland by a company called Lighthouse Dev. And the novel feature of this particular demonstration that took place over about a quarter of a kilometer was that it was designed specifically to be completely eye safe. So if you look at those top two, the rover and the quadcopter, if you stuck your face into that beam, it would be bad news for you. You definitely would not want to do that. The difference with the University of Maryland demonstration is that it is designed to be completely safe. And actually, there's a link there to a BBC program where you can watch about a 10-minute segment or so that discusses this demonstration. And as part of that segment, the host of the program actually sticks his face into the power beam. And of course, he's fine. It's a little bit warm, but he's fine. And part of that is just from the choice of wavelength and the way the system was constructed. In the middle on the bottom, you can see a fixed-wing UAV. This is, I believe, a Lockheed Martin Stalker UAV. And a black square on there, that's the power receiver. The red spot you may see in the middle of the black square is not a laser beam, but rather a beacon for the tracking of this aircraft as it was flying around so that the beam could stay trained on it. And then in the lower right is a picture taken in Seattle. You can see the iconic Space Needle in the background there on the right. And this was just last year. This was part of an effort that I served as a program manager of, where we beamed hundreds of watts, in excess of 400 watts, over hundreds of meters, about 325 meters. And this demonstration was done twice, first in Seattle and then in the Washington, D.C. area at the Naval Surface Warfare Center, Carderock. And there's actually a video on YouTube that shows the demonstration, although it is not too much to see because it's a silent, invisible beam. And I'll actually go into a little bit more detail about that later in the presentation. But first, let's talk a little bit about a different part of the spectrum, which is that microwave, that blue region that I highlighted on a previous chart. And the history for that goes back much further. In fact, some of the most compelling and defining demonstrations of power beaming happened in 1975. It was a bit of a golden year for power beaming, in part because at that point in time, there was a lot of NASA and Department of Energy interest in alternate means of energy because of the oil crisis and the spiking prices for gasoline and energy more broadly. So some of that research that was done at that time was done at Raytheon. The upper left black and white picture here shows what, to my knowledge, remains the most efficient power beaming link that has ever been established, measured from the DC power input to the DC power output of the system. Certainly, and that was at about 54%, carefully and independently verified. In the center of your screen is a picture of what I believe remains the longest distance and highest power beaming demonstration that's been performed to date. This was done in California at the NASA Goldstone Deep Space Network facility, and the dish you see in the foreground was used to send 34 kilowatts to the tower you see on the ridge. There's a white receiver that has a little notch in the top. If you look very closely, you might see, and then below it, below the ridge line, is an array of lights that reflects the amount of power falling on each element of the receiver. If you would like to see more about this, there's a 2-minute video on YouTube. I think the link will get posted in the chat that goes into a little bit more detail on exactly what was done there. And then there's been a lot of effort around the world. And the upper right is a demonstration from Japan in the early 90s, where another fixed-wing UAV was powered by microwaves transmitted from the sport utility vehicle on the road below. And then in the lower left, there was a transmitter put on this airship to actually charge a cell phone on the ground. And then in 2015, there were actually several different notable power beaming demonstrations that were done in Japan at different frequencies and different lengths and powers. I won't go into too much detail there, but suffice it to say that either the Japanese or the Chinese, at least currently, have probably the most advanced microwave power beaming technology. The Koreans have done quite a lot as well, and the US is starting to catch up, but it is certainly a fledgling effort at this point. All right, so let's talk a little bit first about some of the applications. So I've given you a sense of what power beaming is, what's been done. I'm going to talk a little bit now about why people would care. This is the classic, if you're familiar with the Hale-Meyer Catechism, who cares, and why it makes sense to develop this technology. One of the nearest term and greatest interest areas is for drones, right? If you have an electric drone and it's a rotorcraft and it can fly for more than an hour, you're doing pretty good. But a lot of our missions last days, weeks, or months. So having to land it and change a battery or recharge it or have multiple drones to give coverage to a given area is cumbersome and in a lot of instances decidedly suboptimal. So if we were able to keep a drone in the air as long as we wanted, that could have tremendous value. It also means we can make the payload larger, because now instead of lifting batteries to keep us up there longer, we can depend on the power beam as a steady source of energy, and we can instead add a larger sensor package to it. This also gives more flexibility. If it's up there, you don't have to say, oh, you know, I got to make sure that I don't go too far because I'm going to have to land in X number of minutes. It really opens up the flexibility. And the applications are kind of a list of the usual suspects: ISR, intelligence, surveillance, reconnaissance, comms, offboard countermeasures, security for fleets, ports, camps, convoys, and a variety of other areas that I have not listed here. One particular area of interest, and we've gotten a big demand signal from U.S. Central Command for this, is for high altitude craft. So it is possible today to have a high altitude craft that can fly through day and night, but the cost of that is having a very small payload capacity, and also it is not possible at all times of the year and all latitudes because of the availability of sunlight. So the idea is you use solar during the day, you charge up your batteries, you actually gain a lot of altitude and store energy as potential energy. And then over the course of the nighttime, you consume that energy back as you descend in altitude, and then you just have to hope you don't hit the ground until the sun rises and can start powering you and charging your batteries again. So this is another instance where power beaming could be decisive in unlocking a new capability to give us these high altitude platforms in a meaningful way. And then there's a number of terrestrial applications where you could envision, if you have a facility that you need perimeter security for, rather than putting a generator at every sensor or every asset you need to power, you could have a centrally located power transmitter or maybe a primary and redundant, and send power to those places. This also means if you need to be mobile and pack up at a moment's notice, you're not going out and like packing up generators and spooling up cords and things. You can just pick them up, pick up your power transmitter, and go wheels up. So there's a real flexibility aspect to it, and definitely a resilience aspect too, because a power beam cannot be bombed in the same way that a cable can, and it is able to be redirected very quickly. So a lot of different specific applications for that. And we have demonstrated with NRL efforts that it is easily possible to send power over several kilometers effectively. So the groundwork and the sort of existence proofs have been shown. All right, got a little bit of lag there. Okay, so hopefully on your screen right now you have the planetary body power distribution network chart, which shows some of these permanently shadowed regions I mentioned before. They're shown in blue on the chart on the left. And then there's also a close-up of that European rover from an earlier chart, and then a notional depiction of how you might beam power from an orbiting lunar satellite into a permanently shadowed crater. So these are things where, as we really start to gear up for lunar activities, the proverbial moon rush, there's going to need to be a way to move power effectively to these difficult to reach places. And there's probably not much of an appetite to start stringing power lines all over the moon if there is a viable, flexible, resilient alternative. Here's a little bit more about the recent demonstration that I mentioned before. And there is a YouTube video for this, so the link should get posted into the chat if you want to see some more detail on what we did last year. And the key feature of this, much like that University of Maryland one that I mentioned, is that this is completely safe. So there is an integrated system that if an object approaches the power beam, the beam is able to detect that prior to it's getting intercepted and to actually shut off and ensure that power goes where you want it and not somewhere harmful. For both of these demonstrations, we were able to have people come see them and not be required to wear any laser safety eyewear because of the attention that's put into controlling the reflections and various different feedback mechanisms and interlocking safety systems to ensure there's no problem. I'll also mention that the reason you can see the beams in these pictures is because we used an IR sensitive camera. When you're actually at the demonstration, there's nothing to see, there's nothing to hear. It's basically just silent, constant power. And at the Carderock demonstration in particular, we used the energy to run like a simulated security outpost that had computers and lighting and a coffee maker. And by having that wireless connection, it again gives you a lot of latitude in ways that you simply don't have in other ways. The place where we tested is the model basin, so the beam actually was over the water, where if you had wanted to run some sort of cabling for more than 300 meters through a body of water might pose challenges that you simply don't have when you're using power beaming. All right, so to summarize the power beaming portion of this presentation, this is an emerging disruptive technology that many folks just haven't heard of yet. They're not aware of the level to which it is starting to mature. There's a number of breakthroughs that have made this attractive. I won't go into too much detail, but suffice it to say that a lot of the same fiber laser technologies that are now making directed energy more viable also applied to power beaming, and power beaming is in many ways a much easier task than directed energy. And we've gotten a lot of interest, not just from users, but also from the industrial base to put this capability together. Dr. Griffin perhaps said it well at the DARPA 60th anniversary in late 2018 when he said, being able to beam energy from spot to spot in the same way that we use copper wire, that will be very critical. I definitely agree. All right, so space solar, which requires power beaming but is distinct. I'm gonna, for this talk, define space solar as the collection of solar energy in space and its wireless transmission for use on Earth. Now, if you're not familiar with this concept, last year was released a TEDx talk in which I give the context and overview for this, talk about using the sun as a constant, clean, effectively unlimited source of energy, and solar power satellites as a way to make a distribution network that takes advantage of space architectures to get that energy where we need it. So right now, if we have a forward operating base in a remote location, it's a lot of time, a lot of expense, oftentimes risking people's lives to supply energy to that, to bring in fuel convoys with JP8 or liquid hydrocarbon fuel to power that. Imagine how much there would be an advantage if we could instead beam that energy directly from space. Again, this would have the same advantages I described before for power beaming, where the power can be redirected as needed. It's very flexible. It's resilient. So this is something that has been explored for some years, but again, many folks have not heard of it or don't understand the promise of it. And there are significant challenges, which I will discuss momentarily. So here is a schematic depiction of how this might work. And then as you'll see on the upcoming chart, there are a lot of different ways that space solar could be implemented. I don't think there's, at this point anyway, like one clear dominant way to move forward. There's a number of different architectures. But basically, here's how it works. You have the sunlight. It is collected by a satellite. That satellite converts that sunlight into either microwave or laser beam and then sends it to the ground where needed. This picture is not to scale. Historically, most folks have talked about putting these satellites in geosynchronous orbit, but there are certainly many other orbits that could be used. And here is just a quick sampling of some of the many concepts that have been proposed. They go back to the 60s to a patent by Peter Glaser. There's many concepts that were looked at by the aerospace primes in the late 70s as part of the NASA DOE studies for this effort. And many novel concepts have been proposed over the years by creative folks and organizations. Again, I won't go through all of them here, but just understand that there's many different ways that have been proposed. And even just within the last couple of years, there are new proposals and new architectures that people are investigating for solar power satellites that take advantage of different aspects of technology that have gotten more mature over the years. Now, each of these sort of postage stamp concepts is probably going to be able to be broken down into a functional block diagram similar to what I'm showing you here. There's a lot of boxes here. Really, there's just kind of two functions that are happening. One is the solar collection, and the other is the power transmission for the space segment. And then on the ground, you have the power receiver. Important thing to recognize, and I'll mention before I go further, this material, this part of the presentation is based on a study that was released last fall, sponsored by DoD, looking specifically at using space solar for forward operating bases and for military purposes. And the link to that study report, it's 100 pages, 30 the main part of the report, and then a lot of appendices expanding on various points from the report. That is available on the National Space Society website. And like I said, the link should appear in the chat there if you really want to delve into this. I was the editor for the report, and we've received a lot of positive feedback. Obviously, if people find problems or things that we've overlooked, we are eager to hear those. And I always welcome critical and constructive feedback on any of the material that we've put together. So for the functions of a solar power satellite, there's two key areas that do not have the technology readiness that would be needed to implement a system like this. One of those is the solar energy conversion. And you may say, well, Paul, we've been flying satellites with solar cells since the 1950s. Like, how is that not mature enough? The difference is if you go to your local hardware store or big box home improvement store today and you buy a solar panel, it's going to be probably less than $1 a watt. If you want to get a watt of solar for your spacecraft, it's going to be probably about 2 orders of magnitude higher than that. And for solar power satellites, we would need an unprecedented amount of photovoltaics or solar conversion means. And the way that they're made today is simply not at the scale that would be required. So that's an area that needs attention. And then the power beaming also has not been demonstrated at the scale that is needed for solar power satellites. Like, other than that one demo from 1975 at the Goldstone facility, there's not really been too much at a scale that starts to approach. And I'll make this clearer moving forward as I show you some plots on this. So these are the two things. And I'll just briefly mention the framing and motivation for this study that we did. We wanted to look at space solar for DoD, identify the opportunities and challenges, and make actionable recommendations, which we did. And I'll summarize here, and you can, again, consult the report if you want additional detail. So our summary findings were resolving, there's a lot of unresolved challenges, there's a lot of opportunities. The place to start is to retire the risk and further mature space solar collection, power beaming, and its various elements. Look at the different architectures and also examine the possible roles of supporting technologies that might give one architecture an edge over another. For instance, one of the downsides of using something like laser power beaming is it will not go through clouds very well. But if you had a high altitude receiver that was above the clouds and then some means to get power either from there to the ground or to use it at high altitude, that might work decisively in the favor of laser power beaming, particularly because the transmit and receive apertures or surfaces that you need for laser power beaming just because of the physics of the diffraction limit, those can be much smaller than for microwave power beaming. But it doesn't help you if it's critical to get the power to the ground and the laser is being scattered in the clouds. All right, so hopefully you'll have a chart that appears here in a moment. There we go, the opportunities. This is something, because energy underpins everything we do as a country and as a civilization, we need to be thinking about this, right? Like, we largely take energy for granted. The computer you're watching this on is using energy that was produced somewhere that you probably didn't really think about. Most of our energy, even though this is changing, most of our energy still comes from these non-renewable sources at costs in environmental terms and in other terms. So being able to develop and become a master of a new energy technology has enormous significance. So there's also technology dividends that occur not just for energy, but for other things that have implications for our space efforts, for intelligence, and for many other things. And then this also is a kind of a new way of thinking about energy, right? Like right now, if we think we have to move energy, it either is through wires or through moving fuels or some other kind of mass. Power beaming and space solar unlock this ability for you to be able to move energy without having to move the mass. And then there's a huge opportunity in terms of national leadership, right? So like if you look at something like the space station, where we lead a coalition of different countries to do something novel and unprecedented in space, or if you look at something like the International Thermonuclear Experimental Reactor in France that has countries that don't cooperate on a lot of things together. So this is, just in case you're unfamiliar with it, this is a joint effort of the United States, Russia, China, India, Japan, South Korea, European Union. They're all working together to try to unlock the potential of fusion energy, which again would be civilization changing, given our civilization's dependence on energy. There's a similar opportunity for space solar. There's not an ITER equivalent for space solar as there is for fusion right now. So there's a big opportunity there. And then just imagine if we could provide energy to the developing world, if we were working with a country that doesn't have an energy infrastructure, is not grid connected, if we could just beam energy to them for developing their infrastructure, for developing their hospitals, libraries, all the good stuff, that would be a powerful diplomatic tool, right? That's something that we would probably prefer that the United States has rather than another country. So there's a tremendous opportunity there. Now, there are, of course, plenty of challenges, and I have one chart of opportunities and 4 charts enumerating the challenges, so I don't want to minimize the challenges, but it should be clear that the rewards could be considerable, and the risk of not pursuing and not understanding the limits is quite significant, because we don't want to be in kind of the Sputnik situation where it's like, oh my gosh, look what these guys did, we got to play catch up. So without getting too technical, I will mention that a really important parameter for determining the viability of solar power satellites is how much power you can get per unit mass of the satellite. So I have a little plot here. The blue boxes show what we've done at NRL, and we actually launched, Steve mentioned in introducing me, this effort that we have been working on for a couple of years, and that actually launched back in May, and we're just starting to get the flight data from that. There will be a link for that in the chat if you want to see the NRL press release for that, but that launched on the Space Force launch that put the latest Air Force X-37B spaceplane into orbit. So we are starting to look at the actual in-space performance of some of the hardware for this. But those blue boxes show the current specific power, or the watts per kilogram, that we have demonstrated on the ground. And then there's also been efforts through Northrop Grumman and Caltech and the Air Force Research Laboratory. They have a press release from October, you can consult on this, where they are pushing farther forward, building on the work we did to increase the specific power even further. And this is really important, because without getting that specific power number up, it is very difficult to make a technical and economic case for the viability of this versus the alternatives. So I've been talking a little bit about what's been done. There's still quite a lot of tech development to be done. Also for solar power satellites, because you need to intercept sunlight in some capacity, whether it's through photovoltaics or reflectors, you're going to have structures that have a very large area and that have been designed to have a low mass in order to get them into orbit. And they also don't need as much structural mass because there's no gravity, so they don't have to support their own weight. There have been some solar sail missions previously, but there's a lot that remains to be explored there to understand and be able to develop efficient structures for intercepting this light that have this large area and this relatively small mass and the effects of those. There's also the question of lifetime and serviceability. Right now, the largest human-made structure in space is the International Space Station, which was built by a combined effort of people and robots. The satellites we're talking about, in most cases, would be much larger than the International Space Station and almost certainly would be assembled by robots rather than astronauts for a variety of reasons. And there are interesting and notable developments in satellite servicing that will lead to in-space assembly capabilities. One of those is DARPA's RSGS, Robotic Servicing of Geostationary Satellites project, which I was proud to be part of for many years, and that's launching in a couple years here. And it's basically a spacecraft with robot arms on it. So you could see how this could be used for servicing and then perhaps a derivative of that ultimately for assembling large spacecraft like those required for solar power satellites. Now, changing the chart here. Hopefully you guys see that. Okay, so I'm not going to go through all the technology readiness levels, but let me just summarize by saying that some of the lowest technology readiness is on the power beaming side. So that is one of the reasons in the study we recommended a focus there and why investments are being made there. And I think also why you see investments in power beaming being made around the world, recognizing that this is kind of the pole that needs to be pounded first. All right, this is a log chart for power and distance that takes some of the demonstrations that I showed you earlier and puts them all in the same place. So in the upper right, you can see this NASA Goldstone demo, the 34 kilowatts at about a mile, and then you can see a variety of others. Let me highlight just a few of them. I have on the left side that 54% efficient demo that was done by Bill Brown and Dick Dickinson in Massachusetts in 1975. And then I've circled in green the ones that were specifically done with attention to ensuring that there's no hazardous power density. And one of those is actually an Israeli company. The lower left there, Y-Charge, is in the process of getting to market capability. It looks a bit like a smoke alarm or a light bulb you put in the ceiling or on your shelf, and it will find your phone or your smart speaker or your smartwatch or whatever and charge it with an infrared laser beam. And it is actually FDA approved and everything, so they put a lot of attention into maintaining the safety there. I have on the right there on the bottom, the Lighthouse demo at the University of Maryland, and then the power transmitted over laser demo that was done in Seattle and at Naval Surface Warfare Center, Carderock, that's labeled OECIF Patrol. That was sponsored by OECIF, the Operational Energy Capability Improvement Fund, which has been absolutely instrumental in the recent progress that we've seen in the U.S. on this. So hopefully their efforts can continue. Of course, Congress and many of us have financial challenges given our COVID situation. So, but hopefully that's something that can continue. Now I'm going to take that chart from the previous page and shove it into the lower left corner, extending the log axes even farther in power and distance. And now in the upper right, you can see in blue text some of the proposed solar power satellite architectures. And you can see that we have quite a few orders of magnitude in both power and distance to traverse before we can get to those. So the idea now is to start building towards those. And I'll go into that as I conclude here about where we're trying to go and how we're trying to get to that and establish the viability or not of that. So this may be obvious, but one of the biggest challenges for space solar is the economics, right? Like putting anything in space is still expensive. We have really encouraging signs from companies like SpaceX and Blue Origin, who are now like regularly reusing rockets. It used to be said, if we wouldn't have a global air travel market if every time you flew the plane you threw it away at the end. And that's essentially what we've been doing with rockets since the beginning of the space age. But that is changing. SpaceX has rockets that they've used multiple times. Blue Origin has a rocket, not orbital, but suborbital, that they've launched, I think, 6 times. So there is a path towards lower launch costs, but nonetheless, this is definitely a many billions of dollars kind of endeavor. And I think it's important to be clear-eyed about that. Also, in particular, because we're talking about energy, and energy in some sense is fungible. If we had some magic way fusion works out and you can put it in your pocket like your phone, you may see that there's other candidates and other paths that we can get to satisfying our energy needs that don't require space solar. So again, important to be clear-eyed about the possibilities there. On the legal and political side, particularly for spectrum, there is a big challenge. The RF spectrum is essentially full. We put a huge cost on spectrum. There's always a tension between space and terrestrial users on the availability of spectrum. And there's no slot in the spectrum today that stands out for microwave power beaming. And that would have to be established in some way, working through the International Telecommunications Union, which the Japanese have been doing for some years, and in the US through the FCC and NTIA. So this often is overlooked by the folks developing the technology, but would be critical for making this practical. And then there's the safety and perceptions of safety, right? It's not enough for it to actually be safe, but people need to feel safe about it. They need to think it's safe. If you say microwave to someone, they think, oh yeah, that box in my kitchen that cooks stuff. Or if you say laser to someone, they think sharks with laser beams, something dangerous, right? So there's both the actual safety and the perception of safety that would need to be addressed. And I think they can be successfully. Only one thing is underlined in this presentation, and that is this phrase, balancing power density, safety, and utility. This is a little elusive maybe at first, but it's important to understand that you cannot both put a lot of energy and a little bit of energy in a given place, right? Now, if you can't put enough energy into it, it doesn't have utility. If you had a solar panel that was only 0.01% efficient, you wouldn't bother to put it on your house because it wouldn't generate enough energy. If you put 100 suns worth of energy on your house, that wouldn't be attractive either because that would set your house on fire. So there's a balance between the amount of energy per unit area that you put in place to have utility, to be useful, and also to be safe. What we did with the patrol demonstration, that one in Seattle and at Carter Rock, is we figured out a way around this sort of paradox, right? We had a high power density, but then we protected it within a virtual enclosure so that it was safe. You can think about this maybe in the same terms that you think about like the security measures around a nuclear power plant, where we have guards and fences and stuff around a nuclear power plant because you don't want someone walking into the dangerous reactor core. And similar things can be done for space solar and for power beaming. Important to recognize that there are mature alternatives for energy, like especially for DoD. We've been using generators for decades, and displacing those would require having something that can compete either on cost or utility, depending on the context. And then there's also been a resurgence for mobile nuclear energy, which is worth watching, I think. We've seen this story a couple of times. I have a black and white picture from, I forget what year it is, but mobile and small nuclear has been talked about at some length in the past, but is certainly worth investigating and watching. And for any energy system, you need to consider the possible sources of disruption, whether that's from a hostile actor, solar activity, or other sources. These all need to be carefully considered, whether it's space solar or something else. All right, and then finally for the challenges is the schedule. If I went to you in 1960 and I said, hey, the Russians launched Sputnik, I wonder if we could use a satellite system for navigation where people could just have, like in their pocket or on their wrist, a receiver that would receive signals from satellites in a constellation, and they would know exactly where they were anywhere in the world. You would look at me like I was crazy because it would sound like science fiction. And yet that's exactly what we have today. Now, of course, it took several decades to unfold in that way, and a lot of the breakthroughs that were required happened at our government labs. Particularly if you look at the Naval Research Laboratory, we were the first to miniaturize the atomic clocks that were needed for the precise timekeeping for GPS to get them so they could actually fit on a satellite. Something that used to take up many rooms was miniaturized down to something that could actually fit on a satellite. And the military took advantage of this amazing capability for precision guided weapons and for navigation and timing information. And now it's, again, like energy, something we take for granted. You assume that Uber is going to work, or that you can go somewhere and look at your phone and it will tell you exactly where you are, put you on a map. And it's no longer science fiction, right? I'll remind you that even in the 60s, like, rocket failures were still like super common. So the idea of putting up dozens of satellites as we have for GPS today would have seemed also far-fetched at best. So it is possible that that space solar could unfold in a similar way as GPS has. All right, so getting to wrap up here so you guys can ask any questions you have. I think I've covered all these, the maturation of the functional technologies, including power beaming, solar collection is important. We identified quantitative metrics to track the progress to see if we're getting closer to identify where efforts need to be put. And then there's also a tremendous opportunity here to be the leader on this rather than the follower and the dividends associated with that. So here's kind of the roadmap. This is the log plot that goes all the way up to GEO. As we move forward, the first thing to do would be to continue to develop the ground-to-ground capabilities like we did for power transmitted over laser, the Patrol project, and then to extend those into the air and ultimately into space, and that's where these boxes are. So, sorry, I'm not sure why the charts are moving back and forth, but here's a couple closing thoughts, and then I have just one more chart. History is built on contingencies. Energy is critical for all of human activities. As we extend particularly into space and the energy demands of the entire world continue to increase, this is something that needs concentrated attention from countries around the world. And those that move first decisively and proactively are most likely to yield the benefits. And I'll finish with thoughts from the Chinese. This is Wang Ziji, who is the rough equivalent of Robert Goddard, the godfather of rocketry in the United States. He is the analog for China, and he is quoted as saying, "Whoever obtains the technology first could occupy the future energy market." So it is of great strategic significance. And I will thank you for your attention, and I will leave it there, and I welcome your questions. Thank you.
Hey, Paul, thank you very much for that presentation. It did inspire a great number of questions, so we'll go ahead and everybody will answer as many of these as we can in the 10 minutes or so we have remaining, but we're going to stop promptly at 1 p.m. So from Michael Karush, he asked, you mentioned briefly the Tesla experiment, and he asked if there were any similarities between the Tesla experiment with broadcast wireless energy to a remote receiver and the kind of work that you're doing.
What Tesla was doing was not really power beaming because he was not using apertures in the same way, and he was also operating at much lower frequencies. So the comparisons between modern power beaming efforts and what Tesla was doing are not really valid in that sense. So there are, without getting too much into the physics involved, like there are a variety of ways that you can move energy. Power beaming focuses on using electromagnetic waves, and what Tesla was doing was more based on induction and closing circuits through the ground and through the sky in ways that are not strictly analogous. So, and like I said, he was just operating at much lower frequencies in the kilohertz range rather than megahertz and higher for microwaves and optics.
So Paul Danfus and one of our YouTube viewers had similar questions. They're curious about how much power was received or converted at the receiver during the Power Transmitted over Laser project, and then kind of your thoughts on how much power could be transmitted safely.
Yeah, so for the patrol demos we did in Seattle and at Carter Rock near DC, we received in excess of 400 watts. So I think the peak was something like 407 watts. And that, yeah, so that's the answer to that question. In terms of the limit, there isn't really one, right? Because if you have an effective safety system, it becomes less important what the power density is within it, right? Now, you still have to deal with the fact that both the transmitter and the receiver are not 100% efficient in terms of conversion. So there's going to be thermal limits there. Actually, one of the things that we are investigating in our space experiment, the PRAM experiment that launched in May and that we're starting to get data back for, is what levels of concentration and what levels of energy can you realistically achieve within thermal limits. So there's certainly engineering challenges, but I don't think there's a real strict limit, especially since you can always put systems in parallel, right? So like if we had 100 of the same kind of systems that we used for the Power Transmitted over Laser demonstration, we could easily have sent 40 kilowatts, just 400 times 100.
Okay, so from Randall Bradley, he's curious about whether a spiral or a laminate beam would be most effective.
I am not familiar with that terminology. So certainly for photons, in the optical regime, you can talk about the polarization and the angular momentum. All of the demonstrations that have been done so far have been pretty vanilla in that sense. We've looked at it a little bit, but there's not really an indication that changing the angular momentum of the transmission would enhance the energy collection, if I understood the question correctly. So
you brought up the Chinese efforts in the quote at the end. Ezra asks, he mentions the Chinese Academy of Space Technology revealed that China was already testing and constructing an orbital solar farm with the intention of having it functional in the year 2050. Do you have any thoughts on that? Have you heard of anything in the United States similar, or anything else you'd like to offer on that idea?
Yeah, so in 2018, the Chinese announced that they were going to invest $30 million in putting together a development facility for power beaming and space solar in, I believe it was Chongqing province, if memory serves. My colleague, Namrata Goswami, has written a lot of really good articles about what the Chinese are doing. And they publish a lot in the academic literature, and it's clear that they have a multi-pronged approach to this on the microwave side, on the laser side, on the space side, and as do the Japanese and the Koreans. So they seem pretty determined. The Chinese have been pretty reliable in achieving the goals that they set, right? So I'll remind you, for the folks that don't know, the Chinese right now are the only country that have a spacecraft at the Earth-Moon L2 point, so that's on the far side of the moon, and they put that there so that they could support their rover mission. They're also the only country that has a rover on the far side of the moon, which is a significant accomplishment. And these are things they said they would do. They put the resources into it. They laid out the plan. They followed the plan. They executed. So everything changes. Everything iterates. But I am impressed with their ability to do what they set out to do and what they state they're going to do. So if they say, and I think that they want to have an orbital demo no later than 2035, I think, I have no reason to doubt that they are going to charge full speed ahead on this and make good headway. And I think it would be unfortunate if the U.S. was left in the dust on that.
So John Bowling is curious about models that talk about each of the bands you discussed, and they did with a reference to the distance for the transmission and associated losses.
Right. So the International Telecommunications Union has models for atmospheric transmission, which are the transmission as a function of the wavelength. if you're below 10 gigahertz in clear sky transmission, you don't lose that much. And particularly as you go lower in that, if you're below 4 gigahertz, even the rain does not have a tremendous amount of attenuation. And a lot of the DOE NASA studies focused actually on 2.45 gigahertz, one of the ISM, industrial, scientific, and medical bands, because of the very favorable atmospheric transmission and resistance to losses in the rain. So that's part of the frequency selection. As I mentioned, for laser, you have a kind of a different set of bands. I just showed that kind of like pink region, but within there, there's a variety of different bands, and those have been investigated pretty carefully for directed energy and for optical comms transmissions. There's a lot of well-established models, high tran, mod tran, low tran, for finding out the losses that you're going to have. Generally speaking, the less atmosphere you go through, the greater latitude you have in the wavelength you pick. If we're going to do stuff on the moon, you might pick a different wavelength because you don't have to worry about the atmosphere. But I guess I'll just mention that like all of these, there's models for all this stuff that includes all the atmospheric conditions, all the weather conditions. So we have very robust models.
Okay, excellent. Thank you very much for that. So one of the other questions that was asked relates to efficiency of transmission, and Peter Schubert notes that the power and efficiency that you showed on the chart from projects in the 1970s seem to be higher than what we're seeing today. Is there a reason for that? Is there just, you have any thoughts on that?
Yeah, part of it I think is just because people have been focused less on it, right? So the 1975 demonstration that Raytheon did was over about 1.7 meters, so it was fairly short, and there was a tremendous amount of attention put into every element of the chain. The Rectenna receiver had concentric element arrangements that were impedance matched to the expected power density on the receiver. The transmitter was carefully calibrated and selected to operate at a single frequency at high efficiency. And doing an end-to-end effort like that is non-trivial, right? It's a lot easier to pick a single element like a Rectenna element or a Rectenna array and focus on developing the efficiency of that. It's another thing to do that along the whole chain. So I think it is certainly possible to surpass probably by a good deal what was done in 75, but there just hasn't been the focus on it, right? Like a lot of the work that the Japanese did in 2015 was more on things like beam control, right? We didn't talk too much for microwaves about how you might control the beam and ensure it stays where you want to point it. One way for doing that is called retrodirective beam control, and that's a whole separate thing that wasn't done for the demo in 1975, but what would need to be done for these larger scale things. So I think efficiency is important, but it is also a little bit of a red herring because a lot of times people just aren't going to care if they can get the amount of energy that they need. Like, as an example, if you have an application where it's important for a drone to stay in the air forever, they're not going to say, well, you know, it's not efficient enough, because the mission doesn't care about the efficiency. The mission cares about whether it can be done, right? So efficiency is important, but not the ultimate consideration in many circumstances.
Okay, so I think we have time for one more question. Robert Hayes asks about momentum transfer from solar and wind that such large array satellites would have to contend with. Do you have any thoughts on that?
Yeah, definitely. Well, and that gets back to one of the challenges I highlighted, which is these large area to low mass ratios, because it effectively starts to sound like a solar sail. So the effect of the solar wind is not going to be negligible in a lot of these cases. People have looked closely at this. There are quite a few academic papers that examine the effects of not just the solar wind, but also the perturbations that you would expect from the lunar gravity and solar gravity in GEO. One of my colleagues in the UK, Ian McNally, actually wrote his dissertation in a really long paper about something called geosynchronous Laplace plane orbit, which seeks to balance the effects of solar wind and solar pressure with some of these gravitational perturbations. So it definitely can be addressed, but it's going to be in the details of the implementation. If you have a smaller collector or a constellation, maybe it's less of a concern. It's going to depend on the rigidity and the modes of your structures. So I think it is something you can't ignore, but is not insurmountable.
Thanks again, Paul, and thanks to everybody for just the overwhelming number of questions. I regret that we couldn't get to them all, but again, thank you for your interest and participation. I'd also like to thank you again for joining us today under what are at best challenging circumstances and taking time out of what we know are busy schedules to spend your lunch hour with Dr. Jaffe and the HDIAC team. As I mentioned at the beginning of the webinar today, slides and recording this presentation will be made available for download at www.hdIAC.org. If you're interested in learning more about the HDIAC or getting involved as a subject matter expert, presenter, or expanding your presence in our user community, please feel free to reach out directly using the contact information that you'll see on the left-hand side of the screen in the chat box. In addition to these monthly webinars, the HDIAC also offers bi-monthly podcasts that span the range of 8 technical focus areas. We also put out a bi-weekly email digest with the latest scientific and technical news in the Homeland Defense community of practice, as well as a free technical inquiry service where we'll answer questions for you with 4 free hours of research and consulting. Finally, if you're active in the Homeland Defense community and are interested in joining our subject matter expert community, please reach out to us directly. Our subject matter experts contribute in a variety of ways, such as presenting webinars as you saw today, providing podcasts, and consulting as needed on those free technical inquiries that I mentioned. I'd ask that you take time to perhaps join us on 13 August for our next webinar, which is small nuclear reactors, and that will go at 11 o'clock on 13th of August, and again cover Project Pele and small nuclear reactors. And then, Paul, I would like to point out that Dr. Jaffe has also provided us an article for an upcoming state-of-the-art report that we're putting the finishing touches on. We would expect to be out in the next month or so, and that's going to cover alternative energy and a range of energies to include, such as Paul has talked about today, as well as other sources such as geothermal, nuclear, and that type of thing. So be on the lookout for that. Again, our contact information is included in the chat box on the left-hand side of the screen. Thanks, everyone, for their time today. Thank you, Paul, and best regards, and stay well.